Here we have the formula equation for a reaction and solution of two ionically bonded compounds, potassium sulfate, barium nitrate. They are both dissolved in water, indicated by the AQs. When they react, they yield potassium nitrate, staying in solution, staying dissolved, AQ, and also yielding barium sulfate, a solid, which will precipitate out. We are going to rewrite this as an overall ionic equation, which will show how these compounds are actually dissolved in the water. And we're going to use that to determine the net ionic equation, during which we'll also be identifying spectator ions. Each of these compounds contains a polyatomic ion. It's the SO4 right here, it's the NO3 right here. What's a polyatomic ion? It's essentially a covalently bonded molecule that acts like an ion. So in the case of K2SO4, there's two parts that I'm trying to make more clear by the use of these parentheses. You have two potassium ions, indicated by the two that you've got two of them, and you have one sulfate polyatomic ion. And they are essentially magnetically attracted to each other because your potassiums have a positive charge, your sulfates have a negative charge. Here's what it looks like on a molecular level. Here's your sulfur with your four oxygens right here, covalently bonded together. So all of these, the oxygens and the sulfur, are sharing electrons, and these are very, very tight bonds together. You cannot separate the sulfur from these oxygens just by dissolving it in water. That water is not polar enough, not reactive enough to separate these bonds. However, here are the potassium participants in this compound, the two Ks. They are only ionically bonded to the rest of this molecule. So you have a combination of bonds in this whole structure here. Covalent bonds between the sulfurs and the oxygen, which are very strong. Ionic bonds between the potassiums and the oxygens here, which are weak. When you dissolve this in water, some water molecules can come along. Here's a water molecule. The oxygen side is negatively charged. Hydrogen side is positively charged. Here's another water molecule. The oxygen, two hydrogens. The oxygen is negative charged. Hydrogen positive charged. And that's going to be enough to pull these potassiums away from the covalently bonded together oxygens and sulfurs. Now we have these free negative charge portions of this polyatomic ion, and so some other water molecules can come along and stick onto those areas too, helping it dissolve. Oops, I did that wrong. I'll redraw it right here. So what's happening is this potassium is separating from the SO4. You just treat this SO4 like one giant ion. The S's and the O's do not come apart. All right, so I know I'm going to form potassium ions. They're going to be dissolved in solution. I need to indicate the number of potassiums with a coefficient, and I also need to indicate the charge of the potassium ions. I can go ahead and find the number. Right down here, I can look at my subscript. I've got two potassiums, so I can just take this 2 and put it in front as a coefficient. What about my charge? Well, the first ion in your ionic compound is going to have a positive charge. How big is that charge? Is it +1, +2, +3? There's a couple ways you can tell. If you've got a periodic table, you can find your potassium and use your periodic table skills to say, like, okay, my group 1 elements here have one valence electron in that S shell, which they want to lose to become more stable. Potassiums will lose this one valence electron and gain a charge of +1. You can figure it out that way. You could Google it up. What's the charge of a potassium ion? But what if you're in the middle of the lab and you don't have your periodic table handy, you can't search something up? Well, you can tell, as a rule of thumb, by looking at the subscript for its neighboring ion in the ionic compound. So I don't look at the subscript of the S or the O here because we're just treating the SO4 as one giant ion because they're all tightly covalently bonded together. So the real subscript is right here. it's an invisible 1, because by convention, when the subscript is 1, we just leave it out. So the subscript of its neighboring ion will be the charge. What does that look like? Well, I see right here, the neighboring ion for my potassium is SO4. Its subscript is 1, so my charge for my potassium is 1. What about the sulfate ion? I'll go ahead and write it here, SO4, aqueous, still dissolved. Do I have a coefficient? If I have a subscript here, I need to turn it into my coefficient, but my subscript is 1, so my coefficient is 1. By convention, when it's 1, you don't need to write it in. It is the second element, or the second portion of my ionic compound here, so it has a negative charge. First one will always be positively charged. Second one will always be negatively charged. How big is that charge? 1, 2, 3? Well, let's figure it out. Maybe you can do some wizardry with your Lewis diagram of your covalent bonds and figure out what that charge would be, but that's kind of hard. A better way is just find a list of polyatomic ions. It's going to be hard to see. Most periodic tables used for classrooms have a list of common polyatomic ions. Most of them are negatively charged. A few of them are positively charged. So I can look it up and say, oh, my sulfate, here it is right here. It has a charge in -2. So you can put that on right there to find your charge. What if you don't have a periodic table? Well, again, you can use the method that we use for our potassium and look at the subscript of its neighbor in the ionic compound, and that will give you the charge. So just like we saw, okay, for my potassium, the charge is going to be the same as the subscript for its neighboring ion here. So the subscript was 1, so the charge for my potassium is 1. Same for my sulfate. The subscript for its neighbor is 2, so I can generally assume that the charge for my sulfate ion is going to be a 2. Sure enough it is, which we confirm by looking at that periodic table. All right, let's break apart this barium nitrate here. Show how it disassociates when it's in solution. So I'm going to look at my barium. That's aqueous, it's dissolved. Do I need to put a coefficient on here? Nope, there's no coefficient in the formula equation. It has no subscript, so I've got 1 barium here, so 1 barium here. What's this charge? Well, it is the first portion of this ionic compound. Since it's the first, it's going to have a positive charge. How big is that charge? Well, you can use Google. You can use your periodic table and say, oh, barium right here is I know that my group 2 elements want to lose 2 electrons from their valence shell, which will cause it to have a +2 charge. You can figure it out that way, +2. Or again, you can look at the subscript of the neighboring ion in the ionic compound. Right here, our neighboring ion is a polyatomic ion, NO3. Remember, we treat your NO3 as one big ion by itself. So I'm not looking at the subscript for the N. I'm not looking at the subscript for the O. I'm looking at the subscript for this overall polyatomic ion. These are all covalently bonded together. They will not break apart in water. So my subscript there is 2. And like we said, the subscript of the neighboring ion in the ionic compound can give you the charge of the other one. So what's my charge for my barium? Let's look at the subscript of the neighbor. It's 2. So charge for my barium will be 2+, which matches what I would have gotten from the periodic table. All right, let's do that nitrate. NO3, aqueous. How many do I have? I've got 2 of them in here, so I need to put a coefficient of 2. What is my charge? Well, it's the second one in the compound, so I know it's got a negative charge. How big is it? It's 2 things I could do. I could look at the subscript of its neighboring ion, which is 1, and deduce that the charge for this ion is probably 1. I can also look at my list of polyatomic ions. Let's find nitrate. And here it is, a nitrate right here. Sure enough, a charge of -1. So double confirmed. By convention, you don't have to write the 1 here. I'm just writing it for clarity's sake. All right, let's look at our products. KNO3. Again, you've got a K ion here. This is another ionic compound. One of your ions is K, potassium. The other one is a polyatomic ion, NO3. I'm treating that NO3 just like one big ion because they are covalently bonded together. So my K, when I write it, it's aqueous, it's dissolved. I see how many Ks I have. I have 2, so I'm just going to carry this coefficient down here. It's the first one in the ionic compound, so it has a positive charge. What's that charge? Let's look at the subscript of its neighboring ion. Remember, its neighboring ion is not the N, it's not the O, it's the NO3 altogether. So imagine some invisible parentheses there. And its subscript would be 1. And there's just one NO3 ion here. So we'll take that subscript, that should indicate the charge for your K. And again, it will be just the same as it was earlier in the reaction. What about your NO3? Remember, we're treating it just like one big ion. I have a coefficient of 2 right here. That means I have 2 NO3 ions. So I'm just going to carry that 2 on over. It's the second one in the ionic compound, so it has a negative charge. How big is it? Well, let's look at the subscript for its neighboring ion. Subscript is 1, so it'll be a charge of -1. Notice this is consistent with the charge that we found in the reactants for nitrate. If I looked at my list of polyatomic ions, I would see that it had a charge of -1. Now we're done with the hard part. We do not need to disassociate barium sulfate. We should not disassociate barium sulfate because it's not dissolved. It's insoluble. It's a solid here. So we just carry it over just like it was in our formula equation into our overall ionic equation. And indicate that it is solid. It will precipitate out. All right, so here we are. We're done. This is our overall ionic equation. 2K plus a SO4 plus a Ba plus 2 NO3s yielding these products here. That's our overall ionic equation. That's showing us what's really happening inside our test tube during this reaction. All right, how about net ionic equation? Actually, let's talk back up and talk a little bit about what's happening here. So when you take your K2SO4 and dissolve it, those ions spread apart just like this. They're bebopping around, getting attracted to water molecules, getting reattracted to each other, getting attracted back onto water molecules, bouncing off of each other. Same for your barium nitrate. Those ions come apart, sticking onto water, bouncing into each other, bouncing into these K2SO4s. What happens when your free potassium from your K2SO4 bumps into a nitrate ion? Like this one's positively charged, this one's negatively charged. They will attract to each other, and they will form KNO3, just like we see up here. But why don't we see any KNO3 precipitate out after we are done with our solution? Because it turns out KNO3 is soluble in water. As soon as these things find each other in the solution and might attract to each other and adhere, they will be pulled back apart by the water that is in there. They will not stay together, so you do not see them precipitate out. However, when these barium ions encounter a sulfate ion and briefly stick together, well, it turns out they are no longer soluble because barium sulfate is not soluble. They will stick together and suddenly precipitate out of solution and not be in there bouncing around anymore. More of the bariums will find more of the sulfates and precipitate out, and so on until eventually there's none left. And all you've got is just this soup of water and potassium and nitrates floating around in there. So how do we represent that? We represent that by showing the net ionic equation. And we get that by looking for any ions that remain unchanged from the reactants to the products. For example, we have 2 potassium plus 1s in the reactants. We have it in the products. If it is there unchanged in both the reactants and the products, you can cancel it out. Sulfate, here it is in the reactants. It has been changed in the products though. It is stuck onto a barium. So we can't cancel sulfate out because it has done something different between the reactants and the products. Same for barium. It's a free ion in the reactants, but in the products, it's adhered onto a sulfate ion, so we can't cancel it. Our nitrates, however, they are loose, dissolved in the reactants, and here they are, loose, dissolved in the products also. They are exactly the same. We can cancel them out. And when we rewrite this without our canceled out ions, so I'm just going to copy the same equation over. I'm going to copy my overall ionic equation, but I'm not going to copy the ions that canceled. I'll be left with SO4, 2 minus, plus barium, 2 plus, yielding BaSO4, solid. Generally, by convention, if you were writing this standalone, you would put your positively charged ion before the negatively charged ion, but it doesn't matter. So what do we have here? So this, when we showed the dissociation of all of our ions, that was our overall ionic equation right here. This version of it, when you do not include the unchanging ions, this is your net ionic equation right here. Net ionic equation. It is only showing you the things that actually changed in the reaction. What did we eliminate? These right here are K pluses and our NO3 minuses. Those are the spectator ions. Just like if you were at a football game, yeah, you're there at the game, but you're a spectator. You're not participating in it. So yeah, we can see in the overall ionic equation, these potassiums and these nitrates, they're there in the reaction, but they're not really participating in the reaction like the sulfates and the bariums are. They're spectators. So these will be your spectator ions. I'll put this here so you can see the entire thing. I hope this was clear. Have fun.